Here are some conceptual questions about projectile motion. To get the most out of this, you should stop and think about what your own answer is and make a choice before you watch the explanation. You'll see a screen like this just before the explanation begins. Here's the first one. This one is a classic. Like, I did this when I was in college. We have here is a plane that's flying at a constant speed in a straight line, and it drops a package, and we're going to ignore air resistance, and the question is, where is the package going to land relative to the plane? When the package is dropped, the plane is flying 300 meters per second east. When the package first leaves the plane, it's going 300 meters per second east. And we're ignoring air resistance. So the package will continue to go 300 meters per second east until it lands. Ignoring air resistance is definitely not realistic in this case, but it doesn't diminish the fact that this effect exists. Like, there's a scene in Pearl Harbor, one of the bombing scenes, where one of the planes is flying over and you see the pilot waits until he is directly over the ship, and then he drops his bomb, and the bomb falls straight down onto the ship. That is not going to happen. I mean, real bomber pilots, of course, know this. They know that they need to drop it before they get there, because even though air resistance will slow the package down some, it's not going to stop it instantly. I mean, now pilots don't have to worry about it. They just have smart bombs that land. You program the GPS coordinates where you want it to land, and it just lands there. Anyway, if we ignore air resistance, it would fall right under the plane. Here's the next one. In this one, we've got a cart rolling at a constant velocity, and while it is doing that, it fires a ball straight up. What happens to the ball? In other words, where is the ball going to land relative to the cart? So a cart is rolling at a constant velocity on a flat track. It fires the ball straight up into the air. What happens to the ball? Well, the cart is already moving when it fires the ball. So the initial velocity of the ball, let's say the cart is going 3 meters per second to the right. Let's say the cart is going 3 meters per second when it fires the ball. Well, when the cart fires the ball is also going 3 meters per second because it's staying with the cart. Well, when it goes up above the cart, what's pulling sideways on it? Nothing. So is it accelerating? No. That means, is its velocity changing? No. It continues to move at 3 meters per second like it was before. It's not accelerating in the X direction. Gravity doesn't pull sideways. And we're ignoring air resistance. Then it falls back down. It's whenever it lands, I mean, regardless of how high you shoot it or how long it takes it to get back down, the cart and the ball are both going 3 meters per second the whole time. If we're ignoring air resistance, and even if you don't ignore air resistance, it'll be close. I mean, it'll be close as long as you're not shooting something really fast or something really high. If it was a cannonball fired 3 feet in the air, it would basically do this. In this one, we're going to drop one ball and from the same height at the same time, fire another ball horizontally. Which one hits the ground first? Okay, so they both start with the same y initial velocity, 0. Because you drop one, you fire the other one horizontally. Horizontal means no y velocity. They start with the same initial y velocity. They start at the same height. They have the same acceleration in the y direction. All three of those things is the same for both of them. If all three of those things are the same, t's got to be the same too. It's that same kinematic equation that we used when we worked the problem. Everything's the same in there, so time's got to be the same too.